Hey everyone, in today's video we're going to talk about section 12.6, which is called, it's about the binomial theorem. And binomial theorem is a formula, essentially, the method for solving, or expanding, I should say, expanding a binomial that's in this form. So like a plus b to some power, right? And so if we look at some ones we kind of know or could calculate, a plus b to the first is obviously just a plus b. A plus b to the second is one we know, it would be a squared plus 2ab plus b squared. If we wanted to do a plus b to the third, we would be taking a plus b squared, which we had here, and multiplying it by a plus b again. And we would distribute it all out, and you could do that off to the side if you want. And when you do that, you get a cubed plus 3a squared b plus 3ab squared plus b cubed. And same thing, if we wanted to the fourth, we would multiply that by a plus b, and we would end up with this expression here. A to the fourth plus 4a cubed b plus 6a squared b plus 4ab cubed plus b to the fourth, right? And so when we look at these, we can actually spot some patterns, all right? And I want you to maybe pause it for a second and see if you notice any patterns. Some of the patterns that I want to point out here are looking at the exponents of a. Let's start with that. If we look at the exponents of a, we're going to notice that, especially if you look at the fourth one here to the fourth power, the exponents of a go from 4 to 3 to 2 to 1, and then really to 0, because a to the 0 was 1, right? And you can see that pattern there the whole time. The exponents of a count down, the exponents of b count up. So here we have b to the 0, then b to the first, b to the second, b to the third, b to the fourth. The exponents of b count up. And then we have this pattern of the coefficients, or is there a pattern of the coefficients? I want to add a plus b to the 0, and if we did that, it would just be 1. So we can see the coefficients are 1, and then 1 and 1, and then 1, 2, 1, and then 1, 3, 3, 1, and then 1, 4, 6, 4, 1, and we kind of write them out like this, and maybe some of you have seen something like this before. It's called Pascal's triangle. There's a mistake there. That should be a 1. 1, 3, 3, 1. That's called Pascal's triangle, and that's the pattern that these coefficients follow. And so when we look at something, we look at Pascal's triangle, we think of these kind of rows. And so the way to create the triangle is you start with a 1, and then you put 2 1s below it. And then every number is calculated as the sum of the 2 that are above it. So if I try to make the third row, or in a way it's called the second row, I'll point that out in a second. I add the 1 and the 1 to get 2, and then I have 1s on the outside always. So 1 plus 2 here, that's where 3 comes from. And then 1's on the outside, 1 plus 3 is 4, 6, 4, 1. So you can create this triangle very quickly on your own if you recognize the pattern of how it's created. Just always adding the 2 numbers above it. So in this diagram here, we have, it labels the rows: 0th row, 1st row, 2nd row, 3rd row, 4th row, 5th row, 6th row. Why do we call that the 0th row? Because if you connect it to the powers of binomial theorem, you see that relates it to the power of n. So this is like n equals 0, n equals 1, n equals 2. Okay. We also think of the kind of elements of the rows counting up from 0. So this first farthest left 1 is 0, like the 0th element, and then 1 first, second, third. couple other patterns to notice. Let me zoom out here. When we raise it to the fourth power here, how many terms did we end up with? 1, 2, 3, 4, 5. And third power was 4 terms. So when we have a power that we raise the binomial to, we'll always end up with 1 term more than that power. So let's use this here, and we're going to use this pattern to expand this very quickly. Instead of having to distribute it all out, it takes so long to do that, we can expand this quickly. And essentially every term that we're going to write has 3 parts to it. And those 3 parts are going to be the coefficient, the a, and the b. So let's start with this. If I thought about my coefficients for the 5th row, you can see up there, a plus b to the 5th means I'm going to use 1, 5, 10, 10, 5, 1. So I'm going to start by writing those coefficients. 1, 5, 10, 10, 5, 1. And then I know that my a is going to start at a to the 5th. It starts at that power. So I'm going to have a to the 5th, and it counts down. A to the 4th, a to the 3rd, 2nd, 1st, and 0. B is going to start at 0 and count up to 5. B to the 0, B to the 1st, B to the 2nd, 3rd, 4th, and 5th. And so now I can simplify this to write out my final answer. A to the 5th plus 5a4b1 plus 10a cubed b squared plus 10a squared b cubed plus 5ab to the 4th, and then plus b to the 5th. Look how quickly we did that. So for something like number 2, I'll help you get set up on the first couple terms, and then I'll pause it, or have you pause it and finish it off on your own. All right, so here we're raising to the 3rd power, so you got to think about what the 3rd row of Pascal triangle is. If you look up, we can see that it's 1, 3, 3, 1. The a part now is 3x, so for each of those, I need to have 3x to a power starting off at 3, and then 3x squared quantity to the 1st and to the 0. So for y, and I'll just start this here, we would start with negative y to the 0. So take a moment, pause the video, finish this problem out, and then we'll check our answer. So how'd you do? We have 27x cubed. That's coming from 3 cubed there. The negative will be to the 0 power, so it stays positive here. Then for the second term, I'm going to have 3 squared is 9 times 3 is 27. And then it's negative y to the 1st, so that's where I get the minus from. So minus 27x squared y. Then I have 3 times 3 is 9, because it's to the 1st power there. And the negative is squared, so we're back to positive. So we get 9xy squared, and then minus y to the 3rd. So this is Pascal's triangle is a great way to do these quickly, but what happens if we have something to a much higher power where we don't want to write 20 rows of Pascal's triangle? Okay, some of you may take that as a challenge, but we don't want to do that. Okay, so we have something that helps us out with this called the binomial coefficient. And it looks like this. It's got this kind of tall parentheses, and another format you might see sometimes is like a little n, a big capital C, and an R. The C stands for combination. This is a combination in probability. It's called a combination. But we actually read this as n choose R. Because in probability, we're taking n items and we're choosing r of them. That formula, remember, n factorial means n times 1 less than n times, and you continue that down until we get to 3 times 2 times 1. You keep just subtracting 1. And it's important to know that if we have 0 factorial, that is actually defined as 1, the number 1. That's just the mathematical definition of 0 factorial, because if you don't have that, lots of stuff doesn't work. Okay, so it's just a formula, and you do need to memorize it, but you'll kind of memorize it pretty quickly here, because on top it's always just the top number factorial. So if we look at problem 3 here, I'm going to have 5 factorial over, and then on the bottom it's the bottom number factorial, 3, so r factorial is 3, and then you subtract them, so it's the difference, times 2 factorial. These are actually kind of fun to evaluate by hand, because I know that 5 factorial is 5 times 4 times 3 times 2 times 1. 3 factorial is 3 times 2 times 1. 2 factorial is 2 times 1. And then we just go cancel crazy here. Okay, so we have the 2's are going to cancel. I'm sure we could say those 1's cancel. And the 3's cancel. So we get, oh, and that 4 and the 2 turn into a 2 on top. And we get 10. 5 times 2. Right? Let's try number 4. In number 4, we'd have the top number factorial over the bottom number factorial times the difference factorial. Now, it can get a little annoying to write out all of this. So something to notice here is if I'm writing out 9 factorial, it's 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1 is 5 factorial over 4 times 3 times 2 times 1 times 5 factorial. And the reason I almost forgot to write the 5 factorial on the bottom is because what's going to happen here? Those are going to cancel. All right, so we're left with 9 times 8 times 7 times 6. Again, it's kind of fun to do these by hand here. I've got a 3 times 2, that's, oops, let's pick a different color. 3 times 2 is 6, so is that. Those are canceling. The 4 and the 8 cancel to become 2. And we end up with, let's see, I have a 1 on the bottom. So I have 9 times 2 times 7. So that is 18 times 7, which is 70 plus 56, so 126. Okay. Well, if we were to do 5 here, we'd see that it's 9 factorial over 5 factorial times 4 factorial, but that's literally the same exact thing as 4. So we're going to get 126 again. And the reason for that is we have kind of a property that says n choose r is going to also equal n choose n minus r. And that's what's happening here. When essentially this number is the same as the difference between them, we get the same result. We can also do these on our calculator, and that's probably what we'll tend to do here more often. So you basically, on a calculator page, go to menu 5.3, menu probability combinations. It looks like this. You type in the top number, comma, the bottom number. And you can see we get 126 there. Okay, moving on. Something interesting happens here when we start using these combinations or these binomial coefficients. If you were to, and maybe if you want to practice, plug them in your calculator, pause it, or do some by hand, pause it. And when you do these all out, we're going to see that you get 1, 5, 10, 10, 5, and 1, which should look familiar, right? And that's because that's from Pascal's triangle. So we can find any row of Pascal's triangle using binomial coefficients. So if I wanted to find the 20th row, I would have 20 choose 0, 20 choose 1, 20 choose 2, skip a few, all the way to 20, choose 20. So I could find any element of that row of Pascal's triangle using this idea of a binomial coefficient. So here's the true binomial theorem, right? And in a way, I don't think you really are going to memorize this formula. It's more the pattern of it. And I think the patterns are really important to notice. So you'll see a lot of the patterns we've already looked at and talked about here, such as how A counts down from n, whatever we're raising to, all the way down to a to the 1 and then a to the 0. How B is going to count up from b to the 0 to b to the first, second, all the way to b to the n. And then we have the coefficients. And so instead of using Pascal's triangle like straight up, we have that it's the binomial coefficients. And so the top number is always whatever we're raising to. So in this case, n. And the bottom starts off at 0 and counts up all the way to n choose n at the end. So I could expand this polynomial here, or binomial, to the 6th power. Instead of writing out Pascal's triangle 7 rows worth, or 6 rows worth, right? We can use this idea of n choose 0, 1, 2, 3. So I end up with 6 choose 0 times square root of x to the 6th times negative 1 to the 0 plus 6 choose 1, and we just keep building this up. Root x to the 5th, negative 1 to the 1st, so you can see that's what we get for our answer there after we simplify that all out. And so what I like to point out and really focus on is that each term has kind of these 3 parts. You've got the coefficient, you've got your a to the 6th, 5th, 4th, 3rd, and then you got your b that builds up from 0 and on. And each of those 3 things makes up one term of our binomial expansion. I also want to point out that in here, for all of those binomial coefficients, I used my calculator to figure those out. All right, so in number 7 here, find the coefficient of the 8th term of 2x minus y to the 20th. Well, clearly we don't want to just write out the whole thing and then just figure out what the 8th term is, right? Let's try to be more efficient. So I know that my first term would have the binomial coefficient 20 choose 0. That's the first term. And I want to know, what would it be for the 8th term? Well, I know it's 20 on the top because that's my power. And building the bottom up, 0, 1, 2, 3. So if the first term is at 0, the 8th term would be 20 choose 7. I also know for the 8th term, I'm going to have 2x to some power. For the first term, it was 2x to the 20th, and I would build down from there. All right. Well, one of the patterns you'll notice, and you actually see it in the formula up above as well, is that the exponent of a is always n minus the bottom number in your coefficient. So we have 20 minus 7 would give me 13 here. But another way I actually sometimes like to figure that one out last, because the other fact that I like to remember is that for my third piece here, the b, I know that this bottom number is always that exponent. And then my 2 exponents on top have to add up to 20. So then I build the 13 in there. So then to figure out my final answer here, I'm just going to use my calculator, and again, I'm just worried about the coefficient. So I need to know what 20 choose 7 is, and I need to know 2 to the 13, and I need to know negative 1 to the 7th. So when you do 20 choose 7 on your calculator, you get 77,520. And when you use 2 to the 13th, we're going to get times 8,192. And yes, we would get x to the 13th, but all I care about right now is the coefficient. And then negative 1 to the 7th is going to be negative 1. So my coefficient here is going to be negative 635043840. There you go. If we were to expand that all out, that would be the coefficient of the 8th term. Now, a question I'm more likely to ask, rather than saying like the 8th term or the 30th term or the 14th term, I'll say find the x squared term in the expansion of x squared plus 1 over x to the 13th. So to do this type of problem, I like to give myself the template for a term. I know it's going to have the binomial coefficient, I know it's going to be x squared to some power, and I know it's going to be 1 over x to some power. And those powers have to essentially combine to be a final of x squared. So let's build up what we know. I know that I'm going to have 13 here. Right? And I know I'm going to have some bottom in the number. Maybe let's call that r and choose r. So we'll have that r. And because of that, I know that this exponent there is r, which would make the exponent on x squared 13 minus r. Well, I know that this part of this, where the x's are involved, that'll have to combine to be x squared. So I can kind of do a little side equation. I've got x to the 13, x squared to the 13 minus r times 1 over x to the r should equal x squared. And we can kind of just go through and do a little bit of algebra here. This is going to be x to the 26 minus 2r times 1 over x to the r equals x squared. And that's going to give me, I subtract those exponents because I'm dividing. So 26 minus 2r minus r would equal 2. Another way to think of that is this 1 over x to the r is x to the, x to the negative r. And that means, what is this going to be? Negative 3r equals negative 24, which means r is going to equal 8. All right, so I figured that out. So now I can say that I have 13 choose 8 times x squared to the 13 minus 8, which is 5, and then 1 over x to the 8th. And let's do a little calculation, which gives us 1,287 x to the 10th times 1 over x to the 8th. And look at that, we get 1,287 x squared. And it said find the whole term, so I do that whole answer, not just the coefficient. All right, that is binomial theorem. Thanks.